ever built here at CERN. So we are going from the present and future towards the back. First of all, I would like to propose you a video that is going to introduce you to many more things that we do at CERN. We don't do only LAC and not only final detectors. We do many other things. And after that, I'm going to tell you more about detail about our specific visit. Okay?
Decided to award the 2030 Nobel Prize in Physics to Professor François Anglais at Université Libre de Bruxelles, Belgique, and Professor Peter Higgs at University of Edinburgh, United Kingdom.
Whoa, that was an amazing moment. And the fact that we can enjoy such moments on the web is also thanks to CERN. My name is Lilian Smesa. I'm one of 12,000 scientists coming here to CERN from all over the globe. We work at experiments trying to understand the deep nature of our universe. I'm from Norway, and I work on one of CERN's antimatter experiments. Some of my colleagues even got a Nobel Prize for their work, but that doesn't happen very often. Welcome to the largest scientific laboratory in the world. Come join me on a voyage of discovery to find out more about the scientific achievements and the technological innovations happening at this extraordinary place.
After the Second World War, European science was no longer world class. A small group of scientists envisioned a new laboratory that would not only unite European countries, but also allow them to share the increasing costs of nuclear physics facilities.
Seul un laboratoire bien équipé attire les physiciens expérimentateurs, évite la dispersion des talents européens et suscite l'apparition des forces latentes.
On the 29th of September 1954, the 12 founding member states of CERN ratified its convention, establishing the official birth of the organization with its headquarters in Geneva.
Sur le terrain même que l'actuel occupant semble céder avec bonne grâce, et outre et le printemps prochain célébrons les premiers bâtiments.
The story of CERN started more than 60 years ago, on a field just like this, on the border between Switzerland and France.
Within a year, the farmland on the Mérin site near Geneva was transformed into a large complex of workshops, offices, and buildings to house two new accelerators. The synchrocyclotron was the first. In 1959 came the proton synchrotron, still in use today. The 1960s, 70s and 80s saw a relentless increase in the size and complexity of the experiments, always pushing technology and human ingenuity to the limit. This truly cosmopolitan laboratory is run by about 2,500 members of staff from over 20 member states who design and build the particle accelerators and ensure their smooth operation. These accelerators are then used by over 12,000 researchers from more than 70 countries and over 100 nationalities. Many non-European countries are involved in CERN programs via cooperation agreements and through the experiments.
The history of CERN is centered on ever larger and more powerful accelerators. But why do physicists need particle accelerators? Why do we want each to be bigger than the previous one? And what is it that we look at with them?
A human hair has a diameter of about 1/10 of a millimeter. If you want to see its atoms, you have to magnify and magnify again 1,000,000 times in all to see deep into its structure. Atomic nuclei are made of protons and neutrons, with electrons orbiting around them. Protons and neutrons are made of quarks. Quarks and electrons are the fundamental building blocks of the matter we know.
Everything around us and inside us is made of these particles, which stem from the very beginning of our universe. But how do we study these particles and the forces that hold them together inside every form of matter we know of? Well, with very special microscopes. The principle is simple. We use particle accelerators to smash matter together in order to recreate the conditions of energy and density existing in the first instance of our universe, 13.8 billion years ago.
Today, CERN is home to the largest and most powerful particle accelerator in the world, the Large Hadron Collider, or LHC, where we accelerate and collide beams of particles such as protons or lead ions. The journey of the protons begins with a bottle of ordinary hydrogen gas. The hydrogen atoms are stripped of their electrons, leaving their protons ready to be fed into a series of linear and increasingly large circular accelerators, gaining energy and momentum at each stage before finally entering the LHC at very nearly the speed of light. When we collide these particles inside the LHC, the energy from the collision is concentrated in the tiniest and emptiest possible space in the accelerator's vacuum pipe. This is where the most famous scientific formula in the world, E equals mc squared, comes into play. At the heart of the LHC's detectors, the energy from the collision spontaneously transforms into the mass of hundreds of new particles which were not present before. Collisions at the LHC reproduce the conditions that existed a trillionth of a second after the Big Bang, in the first instance of the universe. How do we detect these new particles? By measuring their path and energy with special detectors built in layers around the collision point. The LHC detectors are extremely fast three-dimensional cameras with almost 100 million sensors taking up to 40 million snapshots per second with incredible precision. In over 60 years of existence, CERN has played a vital role in understanding the innermost structure of matter thanks to its research with particle accelerators and detectors, which have provided the overall framework to explain the basic constituents of matter and the forces that act upon them. This framework is known as the Standard Model of Particle Physics.
The Standard Model of Particle Physics describes all known particles and their interactions. Admittedly, it has a rather boring name. It should be called something like the Amazing Theory, because it is the most accurate scientific description of reality to date.
The discovery of the Higgs boson, the final piece in the puzzle of the Standard Model, announced at CERN on the 4th of July 2012, was a triumph for particle physicists at the Large Hadron Collider.
For me, it's really an incredible thing that has happened in my lifetime. It's taken.
A success recognized by the awarding of the 2013 Nobel Prize in Physics to two of the theorists who had first imagined the Brout-Englert-Higgs mechanism.
After 60 years of research, we can say that we know with great precision what all observable matter is made of and how these particles interact. But do we really know everything? What's next?
What is dark matter? Why is it important? Well, it's important because when we ask what the universe is made of, there's three primary things. There's one, stuff that is all around us and what we're made of. There's dark matter, and then there's something called dark energy. And the stuff that we're made of is only a few percent of the total energy of the universe. Dark matter is about a quarter, 25%. Dark energy accounts for the rest, so about 70%. But dark energy is something that we haven't been able to come up with a way to study at CERN. So we can go and study the next largest chunk of the universe, dark matter.
I think the greatest discovery that we could make would be something completely unexpected, something that no theorist has written down yet.
The LHC is now running at almost twice the collision energy and with higher intensity than in 2012. Scientists hope that the LHC experiments will help to further explore these and many other questions in our understanding of the universe at its most fundamental level. In its unending quest for knowledge, CERN has pushed back the frontiers of technology by developing new tools for its research. Much of this innovation has taken place in-house, with many new technologies finding applications in our daily lives.
As you might remember from the beginning, CERN is the birthplace of the World Wide Web and developed an early type of touchscreen way back in the 70s.
The colossal amount of data generated by experiments at CERN and the unprecedented need for storing and distributing them to the world for analysis have pushed computing technologies to their limit. Today, about 500,000 processor cores are required to analyze the data produced by the LHC collisions. This requires the interconnection of more than 170 data centers around the world in what we call the worldwide LHC computing grid.
But let's be clear, our core business is fundamental research of particle physics. By pushing the frontiers of knowledge further every day, physicists push technologies to their limits and even invent new ones to make their experiments work. In this way, CERN has contributed to many technological innovations, from the web to grid computing to more accurate methods for diagnosing and curing diseases like cancer, and much more.
Training the scientists, engineers and technicians of tomorrow is one of CERN's fundamental missions. Every year, CERN trains between 500 and 1,000 university and graduate students. Over 10 years, CERN's teacher programs have reached 11,000 high school teachers and potentially over 1 million of their students. Science education and peaceful collaboration have been among the core values of the organization since its very creation.
Since its birth in 1954, CERN has allowed nations to communicate through the language of science, unconstrained by national borders and in spite of political tensions. Its model of cooperation, originally dreamt up to rebuild Europe's research capabilities, has now become global and remains an example to others.
This was our introductory video. I hope it gave you, as promised, an overview of how many activities we